The screen is visible now?
Yes, sir.
Visible, right? Okay, fine. So today we will do write down, first of all give a heading that calculate calculate the oxidation state calculate the oxidation state of central metal. Okay, calculate the oxidation state of central metal. Fine. So you already know what is the formula. So we have a formula. Okay, yesterday we have done this formula. What is the formula? C is equal to
M plus F.
C is equal to M plus F. This is the formula. So you have to find out the oxidation number or oxidation state. So suppose initially I have this compound 1 2 3 4 5 6 7 8. So this is a 8-membered ring. Okay, you have uranium here 1 2 3 4 5 6 7 8. This is also 8-membered ring you have. So now find out the oxidation state for uranium here. So first of all you have to see this 8-membered ring, right? This is what? This is your cyclooctatetraene. Okay, cyclooctatetraene. So not tetraene. Suppose you have this bond, here you have double bond, right? So now see, so basically you have this, right? So this double bond, if I am drawing like this, so that means all the bonds are involving, or all the atoms are involving in donation to the metal center, right? Now this kind of compound, how can I break? Suppose I have to break the metal carbon bond, how can I break? So here you have actually two possibility of this cyclooctatetraene compound. Either this compound can exist like this, okay, or another possibility is that based on the cleavage of your metal carbon bond, you have two possibilities. So this is one possibility, this is another possibility. Okay, if you break the bond like this, so that time you will get this. If you break the bond like this, so that time you will get this. Okay, now if you see 1 2 3 4 5, so this is also 10 pi electron, and here also you have 6 pi electron. Both are aromatic system. Okay, but when they have done computational studies in that seat, okay, in research basically you will do, okay, computational study. So that time they have shown that this compound is becoming more stable. Okay, this form is actually more stable compared to this form. Both are aromatic systems, but comparatively this compound or this form is more stable than that. Okay, so basically here we will consider that what this compound, from this part, for this part you are getting -2 charge, and for this ring you will get again -2 charge. Okay, so again I am writing this what C charge will be what? Charge will be 0. Overall charge is 0 because it's a neutral molecule. Oxidation state we are finding, so M. And formal charge will be -2 for this ring and -2 for this ring, so overall -4. So M is equal to +4. Okay, so here the oxidation state of this uranium will be what? +4. Is it clear?
Yes, sir.
Clear, all of you? Clear? Here this kind of compound is important. Okay, if you have cyclooctatetraene, so always remember this dianion form will be more stable than your dication. Okay, this is also aromatic, this is also aromatic, but when they did a computational study, they have seen that this compound is becoming more stable compared to that. Okay, fine.
Yes, sir.
Done. Tell me any doubt in this example. No doubt? Okay, fine. So now suppose you have this compound. Now this compound you can do easily. Find out the oxidation state for iron center.
+2.
So basically what? This bond will break like this because you will get one aromatic system, right? If I break like this, you are getting one aromatic system, and if you have to break this bond similarly. So here also what? 0 is equal to M. So -1 for this ring, -1 for this ring. So -2, M is equal to what? +2. So iron is existing in +2 oxidation state. Clear?
Yes, sir.
Okay. Anayana, Smita, clear?
Yes.
Clear, right? Find out the oxidation state for titanium. Find out the oxidation state for titanium.
+4.
+4, right? So again this bond you have to cleave like this. Okay, my voice is breaking or it's fine?
Yes, sir.
Fine, no?
Yes, sir.
Okay, fine. So again this bond will break like this because you will get an aromatic system. So it will be again 0 is equal to what? -1 from each ring. Okay, -1 from each ring. So -4. So metal is equal to what? +4. Okay. See, simple things you can do it easily, but only thing you have to know it properly. Okay, how the bond cleavage you have to do, that you have to know, otherwise you will do mistake. Okay, sorry. Suppose I have this. Here I have tungsten. 1 2 3 4 5. Here also I have tungsten. Here I have carbon monoxide. Here also I have carbon monoxide. Do it. Find out the oxidation state for tungsten.
+2.
So basically this is your what? This is your cyclopentadienyl ring. Okay. Okay. See this 5-membered ring, how it exists. If I am writing like this, na, I am making a circle. So that means it is existing like this. Okay. It is existing like this. And what is the meaning of this circle? So that means all the atoms are donating electrons to the metal center. So it will be eta 5. Okay, here if you see, here only one carbon center is attaching with your metal center, so it will be eta 1. Here if I draw like a circle, so that means eta 5. All the carbon atoms are attaching to the metal center. So same thing. So minus 1 for this ring, minus 1 for this ring. CO is a neutral ligand, so it will be 0. CO is a neutral ligand, it will be 0. So basically 0 is equal to metal minus 2. So M is equal to what? M is equal to plus 2. So here the oxidation state of tungsten will be plus 2. Is it clear? Clear?
Yes, sir.
Clear, right? Okay. Next you have, okay, see, if anyone is getting confused in any topic, okay, so just stop me and then ask me, okay?
Okay, sir.
Hmm. This one. What is the oxidation state of ruthenium?
+2.
Plus 2. CO, check the nature of the ligand.
Or +4, one of the two.
See, if double bond is donating electrons like this, na, that time it will consider as a neutral ligand. But if double bond is attaching like that, so that time what? You can do heterolytic cleavage, na. You can do that time heterolytic cleavage. Okay. So chlorine is what? Chloride minus 1. For this chlorine center, you will get minus 1. And PCY3, so it is nothing but your PPH3. So you will get cyclohexyl group, cyclohexyl group, cyclohexyl group. 3 electrons are involving here, 1 lone pair left, right? Because phosphorus has 5 electrons in its valence shell, 3 electrons already paired, 2 electrons left, that is the lone pair. So that means what? It's a neutral ligand. So for PCY3 the contribution will be 0, this PCY3 contribution will be 0, and this bond you can break like this bond also you can break like this. So overall you are getting minus 2 contribution from this carbon center. So what I am getting, 0 is equal to metal minus 1 and minus 2, so that means minus 4, right? So M is equal to what? Plus 4. So ruthenium oxidation state will be plus 4. Clear? Clear? Done?
Done, sir.
Done, right? Okay. Now suppose I have this one, CH3 manganese CO whole 5. Find out the oxidation state for this manganese.
-1, sir.
Minus 1. It's pretty easy, right? Carbonyl was what? Neutral ligand, so it will be 0. For methyl, you will get minus 1. So what? 0 is equal to M minus 1. M is equal to what? Plus 1.
+1.
Okay, so plus 1, not minus 1. Okay, oxidation state will be plus 1. Okay, if I have this molecule, find out the oxidation number for iron center.
+2, sir.
What?
+2.
Plus 2, right? So again carbonyl is a neutral ligand, right? So here the contribution will be 0 0. For methyl you will get minus 1, and for this cyclopentyl ring you will get minus 1, right? So we have what? 0 is equal to M minus 1 minus 2. So basically M is equal to plus 2. So iron is presenting is Iron is present in plus 2 oxidation state. Clear?
Yes, sir.
Sampriti, clear?
Yes, sir.
Clear, right? Okay. Okay. Now, suppose you have this Pt, Cl3, C2H4 minus. What is the name of this compound?
This salt.
This is salt. Okay. Find out the oxidation state for platinum center. Find out the oxidation state. Huh?
Plus 2.
Plus 2, right? Yeah. So platinum you can consider as X. Okay. Chlorine, what you will get? For chlorine you will get minus 1. So you have 3 chlorine, so that means minus 3. Ethylene, that means what? So I have shown you the structure. Basically it's a square planar compound. Double bond is donating the electrons like this, right? So that's why the double bond here we will consider it as a neutral ligand. So plus 0 is equal to what? What is the overall charge you have? Minus 1. So X is equal to what? Plus 2. So platinum is present in plus 2 oxidation state. Okay, done.
Done, sir.
Done. Okay, next write down this. Suppose you have this compound PD2 DBA whole 3. Okay, so any one of you know what is DBA? What is DBA? Okay, write down. DBA is equal to
Also,
dibenzylidine acetone. Okay, dibenzylidine acetone, and the structure of this DBA will be like this. Okay, structure of DBA is this: dibenzylidine acetone. Okay, dibenzylidine acetone. So basically this double bond is donating electrons to the metal center, and this double bond is also donating electrons to the metal center. Okay, so like that they are actually donating electrons to the metal center. So it will be what? It will be a neutral ligand. Okay, it will be what? It will be a neutral ligand. So if you have neutral ligand, so that means what? You can consider PD2, so that means 2x, and DBA you will get 0 is equal to 0, not plus 2, you will get 0, because it's a neutral ligand. Okay, so neutral ligand means what is the formal charge for neutral ligand? 0. Okay, and overall the molecule is a neutral molecule, so is equal to 0 also. So X is equal to 0, so that means here the oxidation state of palladium center will be 0. Clear?
yes, sir.
All of you clear?
Yes, sir.
Clear, right? Okay, fine. Now what about this example? Find out the oxidation state for manganese.
Plus 1.
Plus 1. So for cyclopentadienyl you will get minus 1, CO will be 0. Okay, so again 0 is equal to what? M minus 1, so M is equal to plus 1. Okay, so here also the oxidation state will be plus 1. Okay, fine, done, right?
Yes, sir.
Okay, fine. uh, So this NO I will say, NO I will say, you just tell me for this is what? This is your cyclopentadienyl, right? Cyclopentadienyl. So for that you will get a -1, and this is your what? This is like that. So you have a double bond here and you have negative charge here. Now this negative charge is basically is in conjugation with that double bond. So how can I write down? I can write down like this. Okay, so basically all the three carbon atoms are donating electrons to the molybdenum center. But the formal charge will definitely -1 for this cyclopentadienyl ring and -1 for this part, this 3-membered linear chain. Okay, now what about this nitrosyl? So write down one thing here, that if you have linear nitrosyl, okay, linear nitrosyl, so this is what? This is your linear, na? Linear nitrosyl. So that time the formal charge will be +1. Okay, linear nitrosyl, the formal charge will be +1. And if you have bent nitrosyl, so that time the formal charge will be -1. And one more thing, if you have linear nitrosyl, that we will donate 3 electron. Okay, and if you have bent nitrosyl, that will donate 1 electron. Okay, now why they are donating 3 electron, why bent nitrosyl is donating 1 electron, that we will do separately later. Okay, in this chapter we will do, but we have to actually know the bonding. Okay, so that basically will take 15 to 20 minutes, so I am not discussing now, we will do it separately later. So just keep in mind, for right now just keep in mind, if you have linear nitrosyl, so the formal charge for linear nitrosyl will be +1, and for bent nitrosyl the formal charge will be -1. When we will do 18 electron rule or electron count, that time also you have to remember that if you have linear nitrosyl, it will donate 3 electron. If you have bent bent nitrosyl ligand, so that time it will donate 1 electron only. So what will be the oxidation number of molybdenum here? So consider molybdenum as X. Okay, so X -1 for this cyclopentadienyl, -1 for this 3-membered, -1 for this bent nitrosyl, and +1 for this linear nitrosyl is equal to 0. So this cancels. X is equal to what? +2, right? So molybdenum is basically present in +2 oxidation state. Is it clear? Any doubt from here? Tell me. Any doubt?
Yes.
All of you clear?
Yes, sir.
Clear, right? Okay. So another small thing is there. Suppose you have this compound palladium, okay, then you have phenyl, and then you have bromine. So what will be the oxidation state of palladium center? So if you,
+2.
+2, right? So if you have phenyl ring, na, so benzene ring, so keep in mind that will always do like that will always attach like that. Okay, carbon palladium bond will form here. So -1 for this, -1 for this. And keep in mind one thing, that if you have carbon palladium bond, so it will not form like this. Okay, always it will form like this. Okay, don't think that all the 6 carbon atoms are donating electrons to palladium. Okay, if I am writing like this, or in exam they are writing like this, so basically carbon palladium bond, so that means it will exist like this. So here the palladium will be in +2 oxidation state. Fine. So that is the end of our this oxidation numbers and those things. Okay, formal charge things. Now next we have, write down bridging ligands. Okay, bridging ligands. So basically we have two types of ligands. Okay, suppose metal center is attaching with one ligand. Y is the ligand, M is the metal center. So that type of ligand is known as what? That type of ligand is known as terminal ligand. Okay, terminal ligand. Suppose okay, we will do and bridging ligand means what? Bridging ligand means the ligand is attaching to more than one metal center. Okay, if the ligand is capable to attach with more than one metal center, that time it is known as your what? Bridging ligand. Okay, that time it is known as your bridging ligand. Okay, bridging ligand. Clear?
Yes, sir.
Clear what is terminal ligand and what is bridging ligand? So if you have bridging ligand, so write down, you need a condition there, at least more than one lone pair. Okay, if the ligand has to be a bridging ligand, so it should be at least more than one lone pair. If it has only one lone pair, then definitely it will be a terminal ligand. But if it has more than one lone pair, that means it is now possible for the ligand, it can be bridging ligand. Okay, it can attach with more than one metal center. Okay, so this bridging ligand thing we actually represent like this mu in coordination compounds. Actually, if I am writing mu, so mu means you have a bridging ligand. Okay, so just write down like this, mu to the power x l. Okay, so what does it mean? So it means that l ligand is attached, a ligand is attached to x number of metal atoms. Okay, so mu xl, so mu stands for what? Mu stands for your bridging ligand symbol. Okay, x means what? X is the number of metal center, with how many metal centers the ligand is actually attaching, that is represented by x. Okay, and l stands for the ligand, what ligand, specific ligand we are talking about. Clear? Clear? Tell me any doubt here, up to here, any doubt? So suppose I have this bond, metal chlorine bond. Okay, so can you tell me the electron contribution in neutral method and ionic method? Suppose chlorine is the ligand, it is forming bond with the metal center. So how many electron donation it is doing in neutral method and ionic method respectively? Tell me.
1 and 2.
Very simple. In neutral method means what? Homolytic cleavage. So do it homolytic cleavage. Okay, and ionic method means what? Hydrolytic cleavage. So there you will get 2 electron. Okay, hydrolytic cleavage means what? The bond is breaking like this. Okay, so 1 electron, 2 electron. Okay, fine.
Yes, sir.
So this is the example of your terminal ligand. This is the example of your terminal ligand. Now see, this chlorine actually can bridge. Okay, so now I will write down one by one. You guys write down with me. Okay, so this is actually a terminal ligand. I am not discussing the bridging. So now write down number 1, that you have to remember this, that octet completion is first step. Octet completion is first step. Okay, so suppose I am writing this. See, now you can tell me actually how many with how many metal centers chlorine can attach. So can you tell me, if I have to fill the octet, how many electrons require here for the chlorine atom?
6 electrons.
6 electrons required, right? Because you know already chlorine has in the valence orbital, it has 7 electrons, 1 electron already involved with bonding with metal, so 6 electrons left. So 2 electrons here, 2 electrons here, and 2 electrons here, right?
Yes, sir.
Right. So when it is terminal, ligand, that time if I am considering neutral method, so it is donating only 1 electron. Now see, when it is becoming bridging, so this lone pair, it can donate to the other metal center, right? This lone pair can also donate to the other metal center, and this lone pair, that also it can donate to the other metal center. So with how many metal centers it can actually bridge?
3.
3. Total how many metals?
4, 4.
4, right? So you have to write down like this, mu 4 Cl. Okay. And if I talk about neutral method, how many electrons are involving here? How many electrons? Huh? For chlorine I am talking about. Ligand center. 7, right? 2, 4, 6, and here you have 1. So 7 electron. If I consider ionic method, so that time it will be 8 electron. Okay. So if I am writing this, that mu 3 Cl, can you tell me how many bonding it is doing now? And
3.
like 3. So that means what? So again, this bond is terminal. Okay, this is your terminal. Okay, terminal ligand. If you are writing this mu 3, so out of this 3, one bond is terminal. Okay, and the other two bond, now see, it can donate this lone pair to the other metal center, as well as it can donate this metal center to this lone pair to the other metal center. So how many electrons it is donating? So 2, 4, 1 from here. So 5 electron in neutral method, and in ionic method I can say 6 electron. Okay, and this terminal bond formation is the first step. Okay, fine. Because anything ligand, if you are talking about any ligand, so that terminal bond is the first step. It have to do the terminal ligand, otherwise bond formation is not possible. Bridging comes next. Okay, bridging is only possible if you have more than one lone pair, or I can say, yeah, there should be some metal also available. Okay, so this is the first condition. Okay, or first example. Now suppose you have NR2. Okay, can you tell me? So it will be terminal ligand or bridging ligand? Hmm?
Terminal.
NR2, terminal or bridging? Is it a terminal ligand or bridging ligand?
Terminal, sir.
Terminal. All of you terminal. How many valence electron nitrogen has? How many valence electron?
5.
5, right? So if you have R2, so that means what? 2 electrons are already involved in what? Covalent bond formation with these two alkyl groups, right?
Yes, sir.
If you have 5 valence electrons in nitrogen, 2 electrons are already involved in bond formation with the two alkyl groups, right? How many electrons left? 3 electrons left. So I can draw like this, na? 1 electron here, and this 1 electron here, right? Now see, this electron, this odd electron, basically what? It can form a bond with a metal center. It can form a covalent bond, na? This odd electron can form a covalent bond with the metal center. So that will be what? That is your terminal. Okay, that is your terminal. So if I am talking about terminal ligand, that time nitrogen is donating how many electrons? In terminal methods, it is donating one electron. This Nr2 ligand, if it is acting as a terminal ligand, that time it is donating one electron. But see, it has a lone pair. Okay, it has a lone pair. So what will happen? It can donate to the other metal center as well. So it can act also as a bridging ligand. Okay, so in a bridging ligand, if it is acting as a bridging ligand, how many electrons it is donating?
12.
3 electron. 2
3.
electron from here and 1 electron from here. Total electron count you have to do. Okay, when you will do 18 electron count, 18 electron rule, that time you have to count the total electron. Okay, so if Nr2 is acting as a terminal ligand, that time it is donating 1 electron. If it is acting as a bridging ligand, that time it is donating all the 3 electrons. Clear? So what are the group members we have here? For suppose you have Nr2, so if I consider Pr2, phosphorus containing, okay, and another is one is your arsenic containing, so they will show you similar kind of properties. Okay, this phosphorus and arsenic also, when they are acting as a terminal ligand, they will donate one electron. If they are acting as a bridging ligand, they will donate all the 3 electrons. Is it clear?
Yes.
Clear? Isa clear? Sampriti clear?
Yes, sir.
Clear, right? Okay, what about this? Suppose you have this ligand pH. Tell me, you guys tell me, terminal ligand, if it is acting as a terminal ligand, how many electron it will donate? And when it is acting as a bridging ligand, how many electrons it will donate?
Sir, at terminal it can donate 2 electron, at bridging 4 electron.
Terminal 2 electron, how you are getting 2? Check again, check.
Terminal 1 bridging 2.
Terminal 1 bridging 2, total electron count. Okay, so again phosphorus is a nitrogen group member, right? So phosphorus has 5 valence electrons. Out of these 5 valence electrons, what you have? It is already forming a bond with the hydrogen, right? It
Yes,
is
sir.
already forming a bond with the hydrogen. So how many electrons left?
4.
4 electrons left. So 2 electrons here and 2 electrons here. Okay. Now if it want to form a terminal ligand, so out of these 2 electrons it will donate only 1 electron with the metal center. Out of these 2 electrons it will donate only 1 electron with the metal center. If it is donating a lone pair, that is not a terminal means covalent bond formation. Okay, covalent bond formation, keep in mind, terminal means covalent bond formation. So how the covalent bond will form? Always it will donate 1 electron, not 2 electrons. Okay, if you are donating 2 electrons, so that means it's a coordinate bond, it's not a covalent bond. Clear? In covalent bond formation, what happens? Equal donation from both the metals, from both the donor atoms, right? Or from both the metals, sorry, both the atoms. So metal is donating 1 electron, phosphorus is donating 1 electron. That is your covalent bond formation, and that is actually your terminal ligand. So 1 electron it will donate. Okay, if it is donating 2 electrons, so that bond will be coordinate bond. So that means phosphorus is donating, metal is taking the electrons. That is actually known as your coordinate bond. Okay, what is the difference between your covalent bond and coordinate bond? In covalent bond you will get equal electron contribution. In coordinate bond you, like the non-metal part will donate, metal will accept the electrons. That's it. Fine. So like this, it is donating 1 electrons like this. Okay, now see, this odd electron, that also can donate to the other metal center, right? That is also possible. huh? So if it is donating, suppose you are getting this structure, for terminal you will get a structure like this. Metal is there, hydrogen is there, 2 electron left, 1 electron left, 3 electrons left. So this is your terminal ligand. Now if it is donating that odd electron, this odd electron to the other atom, so that time it is forming what? Bridging ligand. So I have to show like this now. This is what? This is your mu2 pH. Okay, how many electrons it is donating? 1 electron here, 1 electron here. So write down 2 electron. Okay, anything is possible?
What about the two lone pairs on top?
So that also it can donate now. So another possibility is there. Another possibility is there. So this is what? This is your mu3 pH. Okay. So here how many electrons it is donating? It is acting as a bridging ligand. How many electrons it is donating? 2 electrons from here and 2 electrons from here. So 4 electrons. Clear? So first of all you just fill the octet. Okay, first of all you have to fill the octet, then you have to check. And terminal means, keep in mind, terminal means covalent bond formation. So the ligand will donate only 1 electron. Now apart from this 1 electron, when it is donating further electrons, that time bridging ligand will form. Suppose first of all here 1 electron it is donating, so simply it is forming a covalent bond, it is 1 electron donation. Now when it donates this electron also to the other metal center, it becomes now bridging. Why? Because now it is attached to the two metal centers. When it is donating this lone pair, so that time it is attaching with 3 metal centers. Another structure is also possible. Suppose this lone pair it is not donating directly to the one metal center. This lone pair they are donating like this, 1 electron to one metal center and this other electron to the other metal center. So that time you will get a thing like this, phosphorus hydrogen, and now 4 metal centers are attaching here, 4 metal centers. So that is what? That is your mu4 pH. So here also the electron contribution will be 4 electron bridging 4 electron contribution, but the type of bonding is different. Okay.
What about like carbene? Can we have Pg double bond M?
Carbene. We will
And
come. We will come. We will come to carbene.
No, I'm saying, can we do that with phosphorus? Double bond M. 2, 1 M. Can we have two bonds?
Yeah. Tell me what you are asking. Phosphorus.
Phosphorus and one metal is there. In between
One metal
that,
is there.
you have two bonds between that instead of one. Is that possible?
Two bonds. Where I have two bonds?
Between phosphorus and the metal.
This type.
Yeah. Can that be possible?
So first of all you have to check what is the unit they are giving. Suppose what is the unit I am giving here? pH unit. Okay, pH unit is giving. So first of all you have to write down what is the unit they are giving. So if they are giving pH unit, so write down like this. Now how many electrons left? 2 electrons, 2 electrons. Then you have to check. Now you are saying double bond. So this is actually covalent bond formation, na? So that means this is possible. How is it possible? So that time this one electron, metal also, if metal also have two electrons, same metal, if the same metal center you have two electrons and it is donating one electron, so that time it is possible. And if you have more than one metal centers, that time it will do bridging.
So in all of these, the double bond and the one bridging, two bridging, three bridging, four bridging, the charge will not change, right?
No, charge will not change, because bridging ligand also means what? It is donating lone pairs, right? So when it is donating lone pairs, it is considered as a neutral ligand.
So For all of them, pH will be -2, right?
-2 means
Like if I am considering oxidation state and I want to say the formal charge of pH, what will it be?
formal charge of pH.
Hmm. Formal
uh,
charge will not change, right? Regardless of
no,
bridging or
formal charge will not change. Formal charge will not change because you are donating lone pairs only, that is acting as a neutral ligand.
so formal charge in this case is what?
That you have to check with how many metal centers it is attaching. Okay, because it also depends on the metal center na.
So it can change number of.
um, when it is doing terminal, that time you can say that what pH will have -1 formal charge, because this bond can do, we can do this is heterolytic cleavage. But suppose now this is donating 2 electrons to 2 different metal centers, so that time you can break like this, so that time the formal charge will change -2. Okay, now suppose here it is donating the lone pair, so I am showing it like this is a coordinate bond. Okay, if it is donating the whole lone pair to the metal center, so that time it is a neutral ligand, so here also the formal charge will be -2, it is not changing. Okay, but if you see, if it is donating electrons like this, 4 electrons it is donating to the 4 different metal centers, so that time the formal charge will be -4. Clear what I am saying?
Yeah.
When it is forming a sigma bond, when it is forming a covalent bond, this bond you have to do like this na, heterolytic cleavage you can do. But if you have a coordinate bond, that time you cannot do it. Okay, that
Okay.
will act as a neutral ligand. So if you have a coordinate bond, formal charge will not change, but if you have covalent bond, a sigma bond, that time the formal charge will change.
Okay, got it.
Got it? Okay, fine. Okay, now what about this OR ligand? So this is a ligand. Tell me, in terminal, if it is acting as a terminal, how many electrons it will donate, and if it is acting as a bridging, how many ligand, how many electron it will donate. So first of all, fill the octet, then check.
One and four, sir.
1 and 4,
Four.
4 how you are getting? First of all, see, oxygen has how many valence electrons?
Six electrons.
6 electrons. Already 1 electron is involving in here, right?
And five, yes, sir.
So how many electrons left? 5
Five.
electrons. So 2 electrons here, 1 electron here, 2 electrons here,
Yes, sir.
right? So if I want to form a terminal bond, a covalent bond, this odd electron will take part, right?
Yes,
This
sir.
odd electron will take part in your terminal bonding, right? Terminal ligand. So 1 electron, that is fine. Now suppose this lone pair it is donating to the other metal center, so that time how many electrons it is donating? Total how many electrons it is donating? 2 electrons
Two.
from here and 1 electron from here na,
One.
3 electron. Okay, and that I can write down like what, mu 2 OR. Okay, now suppose this lone pair, you have another lone pair, another free lone pair you have, so this free lone pair it can donate to the other metal center as well. So that time how many electrons it is donating? 2 electrons here, 2 electrons here, 1 electron here, 5 electrons. And that time what I can write down? Mu 3 OR. Clear?
Yes, sir.
Tell me all of you, clear? Any doubt in this ligand, OR ligand? So OR can act as a terminal ligand as well as a bridging ligand. Okay, terminal ligand, all the ligand, okay, all the ligand, when it is actually acting as a terminal ligand, they will simply donate one electron. Okay, but when it actually acting as a bridging ligand, you have to count down the lone pair as well as these electrons also, which is forming sigma bond. So 2 electrons from here, 1 electron from here, 2 2 4 and 1 electron from here, total you have 5 electron. Clear? So that is the maximum possibility of oxygen. Okay, I cannot write down here, I cannot write down like this mu for OR, that is not possible because no electrons now left. Okay, but if you see for chlorine system, that time we can write down mu for Cl. See, we have written because you have that much lone pair. Okay, so that's what actually I am trying to say, or I am trying to teach you, that you have to actually first of all fill the octet, then check the possibility with how many metal centers it can do the bridging. It only depends on its octet. If you have lone pair availability, then only it can donate. Okay, otherwise not.
Sir, mu 5 OR it can't it form?
Huh?
It can it form mu 5 OR?
Mu 5 OR it can form these things, it can form actually if it donate one electron separately. So suppose you have metal, oxygen, R. Now you are saying mu 5, right? So that means this one electron is attaching with one metal center, this one electron is attaching with one metal center, this one electron is attaching with one metal center, this one electron is attaching with one metal center. So that time it can form mu 5. Okay, so that depends totally on the metal center also. Like you will get to know when we will do example, that time you will get to know how it is donating, because when you will do 18 electron count na, that time you have to actually check. If you give that much electrons, so sometime it will cross the 18 value, so that means it is not possible. Okay, that we will come. Clear?
Yes, sir.
Okay. Okay, fine. And suppose I have this ligand, so can you tell me how many electrons it can donate?
Two.
2 electrons, right? Because nitrogen is already forming 3 bonds, so that means 2 electrons left. Okay, so if 2 electrons left, it will donate to the metal center. Okay, so it is terminal or bridging? Is it terminal or bridging? Terminal, because it is only attaching to one metal center. So if you have terminal ligand, that time it is donating 2 electrons only. Okay, suppose you have this, do it.
And 4.
2 and 4. So if it is donating these electrons, so then it will act as a terminal ligand. Okay, so see, initially what are the examples we are doing? There we are doing only terminal is equal to 1 electron, but terminal is equal to 2 electron is also possible when you have no option. Okay, here this nitrogen has no option, it has to attach with only one metal center because all the electrons are already involved, right? And this lone pair it can donate to the other metal center. So if it is bridging, if it is acting as a bridging, that time it will donate 4 electron. Okay, fine. And another thing, suppose you have this. What is the name of this molecule?
Phenanthrene.
Phenanthrene?
Phenanthrene.
No, not phenanthrene. Check.
110. No, no.
No, there is a common name, na?
Diphenyl.
Diphenyl nitrogen is there.
Yeah. Dipyridyl.
Bipyridine.
Dipyridine.
Bipyridine. This is also known as like this BPY. Okay, bipyridine. This one ring is what? If I write only one ring, so that is what? That is your pyridine, na? So two pyridine rings are there, bipyridine, BPY. Okay. Okay, how many electrons it is donating here?
4 electrons.
Total electron. Check total
4
electron.
electrons.
4 electron. It is terminal or bridging?
Bridging.
Bridging. If you say it bridging, then it will be wrong. How many metal centers are there?
1.
1. So it will be terminal. Check the number of metal center. If you have more than one number of metal center, then only it is bridging. Okay, if you have one metal, it is terminal. If you have two metal centers, at least two metal centers you need, then it will be bridging. More than one metal centers you need. Okay, so here also it is acting as a terminal ligand and it is donating how many electrons? 4 electrons. Okay, so terminal ligands can donate 1 electron, 2 electron, 4 electron. That depends on the nature of the ligand. But what you have to check, how many metal centers is attaching with the ligand. If only one metal center is attaching, so that means always it will be terminal. If more than one metal center is there, so that time you can say it bridging. Clear? Clear?
Yes, sir.
Okay. Fine. So now write down number 2. Number 2, what we have? CH3, CH, CH2, hydrogen, CO. Okay, so these are some examples we have. These are some ligands we have: CH3, CH, CH2, hydrogen, CO. So here write down that contribution is same. Contribution is same at bridging. Contribution is same at bridging and terminal position. Bridging and terminal position. Okay, so suppose first of all I am coming with the simplest. You have hydrogen, so I think all of you know hydrogen has only one electrons. So suppose one metal is attaching with hydrogen electron, that time it is donating one electron. Okay, now you know banana bond, right? B2H6 molecule. So their hydrogen coin actually attached with two metal centers also. So that time also it is donating only one electron because it has only one electron, right? So whether it is attaching with one metal center, two metal center, or suppose the hydrogen is attaching with three metal centers, so that time also the electron contribution will be 1. Okay, it cannot do more than 1, cannot donate more than 1. Okay, done. This is what this kind of system is known as what? 3 centered 1 electron, 3 centered 1 electron bond. Okay, Okay, now suppose you have CH3. So CH3 means what? Hydrogen, hydrogen, hydrogen. So carbon has how many valence electrons? 4 valence electrons. Out of that 4, 3 electrons are already involved in bonding with hydrogen. So how many electrons left? 1 electron left, right? So it can do bonding with one metal center. Okay, so 1 electron. So that is your terminal bonding. Now this CH3, it can attach also with 2 metal center. That time also it will donate 1 electron. Okay, fine. Fine. So if you have one electron and the ligand is attaching with more than one metal center, so no need to worry. It will donate only one electron only. Okay, because it has only one electron. It cannot donate more than that. Okay. So suppose you have this compound Al2 CH3 whole 6. See, you have CH3 ligand here. So the structure basically looks like this. So if I talk about this, na, this bond. So this is what? This is terminal or bridging. This bond is what? Terminal or bridging? Terminal. So you have 4 terminal bonds. See, when it is doing 4 terminal bonds, that time also it is donating 1 electron, right? But if you see here, this middle two CH3 groups, they are attaching actually with 2 aluminum centers. So they are actually bridging ligand. Okay, but they are also donating 1 electron. Now how to check? So see, aluminum has how many valence electrons? 3 valence electrons, right? So 1 electron is involving here, 1 electron is involving here. Now suppose 1 electron is involving here and CH3 is donating 1 electron here. Okay, so that time what is happening? So this bond is forming, but if aluminum is donating electrons here, that time CH3 cannot donate electrons here, and here this time this bond, so that time you have CH3 will donate 1 electron here and aluminum will donate 1 electron here. So that is the case. Okay, so this is what, how many electrons you have, how many centers you have, 1 2 3. So you have 3 centered, how many electrons? See, this bond you have no electrons, and here you have 2 electrons. So 3 centered 2 electron bond. Okay, so the same thing, same example with what, B2H6 molecule, you know, right? Diborane, also same thing. So here if you see also, you will get banana bond, and this is what, this is also your 3 centered 2 electron bond. Now why you are getting 3 centered 2 electron bond, that we will separately discuss in your main group elements on that time. Okay, fine, this is clear.
Yes, sir.
Clear, right? Okay, suppose you have this carbonyl ligand. I told all of you that carbonyl, now try to write down like this: oxygen is positively charged, carbon is negatively charged, carbon will have a lone pair, that is actually donating to the metal center. Okay, so first of all it's a neutral ligand, and it's a terminal ligand. Okay, and electron contribution will be 2. Okay, electron contribution will be 2. Now suppose carbonyl, you can see carbonyl, this kind of compound is possible. This will act as a ketone compound. So this is not a ketone, basically it looks like ketone. So here also the electron contribution will be 2. Okay, and if the carbonyl is attaching with more than one metal center, more than one metal center, okay, so then also the electron contribution will be 2. Okay, so see what we have discussing here, that we have this ligand CH3, CH, CH2, hydrogen, CO. Whether they are acting as a bridging ligand or terminal ligand, they are actually donating same number of electrons. So we had discussed about hydrogen, CH3, CO. What left? The two things left, CH and CH2. So let's discuss about the CH and CH2. So if I am drawing CH, so this is your CH. So how many electrons left? 3 electrons left, right? 3 electrons left. So suppose you have only one single metal atom and you have to use 3 electrons. What it will do? It will form a triple bond. So how many electrons it is donating? 3 electrons. Suppose you have CH and now it is attaching with 3 different metal centers. So that time also it is donating how many electrons? 3 electrons. So this is your terminal. This is your terminal. And this is what? This is your bridging case. So see, in terminal and bridging they are donating same number of electrons. Okay, same number of electrons. Similarly, if I talk about CH2, so this is your CH2. How many electrons left for the carbon center? 2 electrons left. So with a single metal atom, it will form a double bond. Okay, how many electrons it is donating? 2 electron. When it is forming what? Terminal ligand. When it is a terminal ligand, it is donating 2 electrons. Now if you have this, okay, if it is attaching with 2 different metal centers, so that time it's a what? It's a bridging ligand, na? If it is attaching with 2 different metal centers, it's a bridging ligand. So that time also it will donate 2 electrons. Okay, so all these ligands, this CH3, CH, CH2, hydrogen, CO, if they are acting as a terminal ligand or bridging ligand, no need to worry. What I am saying, no need to worry, because they are donating same number of electrons. But if you have this kind of ligands, pH, OR, chlorine, so that time terminal and bridging, they will donate different kinds of electrons. Okay, different number of electrons they will donate. But if you have this set of any ligand out of this set, CH3, CH, CH2, hydrogen, CO, they will donate same number of electrons. No need to worry. Okay, clear?
Yes, sir.
Clear, right? Okay, fine. So next we have alkyne. Okay, alkyne means what? Triple bond, right? So suppose you have this triple bond, acetylene molecule, and now this double bond, this pi bond is donating electrons to the metal center. So that will be what? Terminal or bridging?
Terminal.
Terminal. How many electrons it is donating? 2
2
electrons,
electrons.
right? But if it donates the electrons like this, one pi bond donates electrons to one metal center, other pi bond donates electrons to the other metal center, so that time it's a bridging. That time it's a bridging ligand and it is donating how many electrons? 4 electrons. Clear?
Yes, sir.
Clear, right? Suppose you have this ligand NH. Can you tell me, when it is terminal and bridging, how many electrons it will donate respectively?
Terminal 2 bridging 4.
Correct. So nitrogen, first of all, fill the octet. Okay, how many electrons you have? 5
4
electrons,
plus 4.
5 valence electrons. 1 electron is already involved in bonding, so 4 electrons left. So now see, suppose you have only one metal center and you have to form terminal bond, so that means it will form a double bond. Okay, because terminal means what? You need only one metal center. So when it is a terminal ligand, it is donating 2 electrons. If it is forming bridging, so This is what? This is your bridging, na? If it is forming bridging ligand, if it is acting as a bridging ligand, that time it will donate how many electrons? 4 electrons. Clear?
Yes, sir.
Clear? And another ligand is there. These are basically organic molecules. This compound. What is the name of this compound? Any one of you? Okay, I am making it simple.
2, 4.
I am making it simple, so you can identify.
Penta 2, 4 dino.
No, you have a normal name also.
Acetoacetate.
Acetyl.
Acetoacetate.
Acetoacetate. So if you use a base, base will abstract this acidic proton. Okay, because this is the most acidic proton, right? It is in between two carbonyl groups. So base will abstract the proton from here, and what you will get? You will get a negative charge here, right? So now this negative charge will do resonance with this. Okay, so what we will get? Acetyl acetonate. Okay, what we are getting now? Acetyl acetonate. So this bond will break. You are getting a double bond here. Okay, here you have double bond O, here you have CH3. So this is what? This is your acetyl acetonate. Now suppose you have a metal center, so it is donating electrons, it is also donating electrons. Can you tell me how many electrons it is donating?
4.
4
electron.
4 electron, right? Because if oxygen is getting negative charge, so that means how many electrons you have? This. Okay, so it is donating 4 electrons. Bridging or what? Terminal or bridging ligand, it's bridging. How many metal centers are there? Terminal, okay, don't confuse. Done. Tell me any doubt. We are done with this. We are done with bridging ligands. Any doubt you guys have? Any doubt you guys have?
No, sir.
No, right? Fine. So next we have the very popular 18 electron rule. Okay, now all the things will be work out here, that neutral method, ionic method, bridging ligand concept. Okay, all things will be applicable here now. Okay, so 18 electron rule. Okay, so today we will not practice that much example. I am just starting 18 electron rule. Okay, next day we will see examples. Okay, so first of all 18 electron rule. So write down one point, that this is shown by what? This is actually shown by transition metal complexes. Okay, transition metal complexes. Okay, even in interview they can ask from you 18 electron rule. Okay, netgate they are not asking nowadays, but interview they can ask you. Okay, so if you have valence, so how to check? So valence electrons of metal plus electrons donated by ligands. If you add these two, what? Valence electrons of metal plus what? Electrons donated by ligands. So that should be equal to what? That should be equal to 18. Okay, valence electrons of metal plus electrons donated by ligands, and that should be equal to 18. Now basically why we are choosing transition metals, why main group elements we are not considering here, why we are only talking about transition metals. So if I talk about transition metals, and specifically suppose for simplification I am talking about 3D transition elements. So what are the orbitals we have there? 4s orbital, okay, then you have 3D orbital. So 3D orbital means what? You have 5 orbitals here, 1 2 3 4 5. This is your 3D orbital, and next you have 4p orbital. So here you have 1 2 3. So now you can see how many electrons they can occupy. Each orbital can occupy how many electrons? 2 electrons, right? So here 2 electrons, 2 4 6 8 10. Here how many electrons? 2 4 6. So I am getting 2 electrons from here, 10 electrons from here, 6 electrons from here. Total how many electrons you are getting? How many electrons you are getting in total? 18, right? So that is why we are calling it 18 electron rule, and that is only applicable to your transition metal complex. They can ask you in interview that why you are considering only transition metals, why main group element not showing this. Okay, so you have to explain it. Okay, and keep in mind when you are getting this 18 electrons, so basically we have 9 orbitals and you have 18 electrons, and this is what? This is actually closed and stable, closed and stable configuration, because all the orbitals are fulfilled now. Okay, so that's why it's a very stable configuration. Done.
Yes.
Done, right? Okay. Fine. So I think today we don't have that much time, so yeah, it's better that we will continue in the next class. Okay, because now we will have to continue with the examples. So first of all I have to discuss something, then I can go to the example. Okay, so that's it, we are doing up to this. Okay, I am stopping here. So just I am introducing what is 18 electron rule. Next day we will see the examples. Okay, we will do lots of examples. We have around 30 examples we will do. Okay, 30 examples we have, and then lots of example we will do, around 50 examples we will do in the next class. Fine, anything doubt up to this, tell me. Anything doubt from bridging ligand or from the neutral method, ionic method, any doubt you have? No doubt? Isa, Smita, Nayana?
No doubts.
No doubt? Sita?
Clear, sir.
Clear, all of you clear? Okay, okay, what I am saying, okay, see, Sunday I will take a test from electrochemistry. Electrochemistry you have not taken any test, right?
Yes, sir.
So in this Sunday you will have a test from electrochemistry. Okay, time I will mention in the group, most probably in the evening time, and I think ma'am will take class for your physical chemistry, because we have done 2 organic class, 2 inorganic class, right? So physical chemistry left, ma'am will take that. Okay, and if possible I will take extra class, so that is not an issue. But the thing is, Sunday electrochemistry test is fixed. Okay, So
Yes,
prepare
sir.
for that. Okay, and I will share the marks for your what reaction intermediate test. Yeah, that's it. Okay, so prepare well for the test. Okay, the
Okay,
test
sir.
will be usually for 1 hour, 25 questions will be there. Okay, 100 marks test. Okay, test will be for 1 hour, 25 questions will be there, 100 marks will be there. For one question you will get plus 4. Okay, 4 marks. For negative you will get minus 1. Okay, clear? If you are not
Yes.
confident, then skip the question. Don't no need to attempt all the questions. Hmm.
Okay, sir.
Okay, so that's it for today. We will continue tomorrow. Okay, bye.
Bye.
Thank you, sir.
Thank you.
Thank you.
Thank you.